simply by going through the process of writing the inverse of an exponential function. So the process of writing an inverse says to first do what? Switch the x's and the y's. And then do what? Solve for y. Now, when you're solving for a variable that's in an exponent, that's where taking the log of both sides comes in. And you guys did log base 2 on both sides, right? To get y all by itself. It's a little bit different than the way I do it, but I'll get to that in a minute. So you take log base 2 of both sides, and that cancels, so you end up with log base 2 of x equals y, hence the inverse. Right? Okay? So, with all things inverses, x's and y's switch. So if we think of our critical points from yesterday, our critical points were 0, 1, right? And 1 comma b. So our critical points for a log graph, what's 0, 1 going to turn into? 1, 0. What's 1 comma b going to turn into? B comma 1. And our asymptote of our exponential graph yesterday was y equals 0. What's the asymptote of a log graph? X equals 0. All things x's and y's switch. So your critical features of log functions. Okay? So I'm really only going to graph this log one right here. So I have a critical point at 1, 0, and at b comma 1. What's my base here? 2. So 2 comma 1, and an asymptote at x equals 0. Whoops. And there's your log parent graph for log base 2 of x. Your critical points and your asymptotes always need to be there. Now, we didn't talk about it as much yesterday, but if my graph for 2 to the x, really quick sketch, looked like this, what's the domain of that yesterday? Negative infinity to infinity, right? What's the range of that? Y is greater than 0. So when we go to our log graph, again, all things x's and y's are switched. So if your domain used to be negative infinity to infinity, what is now negative infinity to infinity? Range. Can you see that justified on the graph? Negative infinity to infinity for your y coordinates. And if your range yesterday was y is greater than 0, then your domain today is what? X is greater than 0. And you can see that. All your x's are remaining greater than 0. And going to that log function, hopefully you recall from last year, you cannot take the log of a negative number. You cannot take the log of 0. Yes? So the information they were looking for right here, I wrote over here. For g of x, the asymptote is x equals 0. And the points are 1, 0, and b1, which in this case is 2, 1. Now, remember this notation. As my x-coordinates are approaching 0 from the right, so I'm tracing along my function going towards 0 from the right, what's happening to my function value? Good. So really quickly, the reason, and I'll do it with maybe a different, you're not going to see color. Maybe you will. I'll do it with a different color. I initially was going to have you, and you can choose to do this or just to watch, I was going to have you graph both of the f of x and the g of x on the same function. So for my exponential function, my asymptote is instead here. And the points are 0, 1, and 1, 2. The reason I was going to have you do this was going to be to illustrate the symmetry that those two inverses have with each other. Do we see it? Symmetry across the line, y equals x. So really a lot of connections to be made between exponential graphs and log graphs and kind of their relationship via that inverse property. Okay, you can see it with asymptotes, switching from x equals 0 to y equals 0. You can see it with ranges and domains flip-flopping. You can see it with the reflection of when you look at the image. You will be doing a lot of sketching exponential graphs and log graphs in Calc. In fact, I go to Mrs. Hill and Mr. Hill every year and ask, like last year's group, what were they weaker at that you would want them to be better at? And sketching log graphs is something that continuously comes up. So it's a little bit tough here because in the PreCalc textbook it's just a snippet, which you see we do it obviously. I want you to be mindful of the two critical points in the asymptote all the time, and just the basic general format. But we do it in this chapter, and then it really almost never comes up again. So I will be working to include these parent graphs of log functions on your spiral so that that doesn't get stale, so that next year when you guys get to Mrs. Hill, she can say, wow, they were much better at it this year, or Mr. Hill. Okay? So, that would be silly. Why would you be advanced all the while and not take something that you're going to get a 4 or 5 on? That seems silly. It is an option. It's not a great option, though. It's a silly option. Okay. So, just jumping to the bottom quickly here. The x-intercept is 1. Yesterday on exponential functions, the y-intercept was 1. If b is greater than 0, what's your function doing? Increasing. And that was the example. What if b was between 0 and 1? Like what if it was log base 1/2 of x? Well, let's see. What would your x-intercept be? Still 1, 0, right? And what would your next point be? 1/2 comma 1, which would be there, right? So, and here's your asymptote as always, so you can see that it is decreasing. So that's really the same. That is the same as exponentials, right? If your b is greater than 1, that's exponential growth. It's increasing. If your b is less than 1, that's exponential decay. If we're talking exponents, we don't really talk about growth and decay so much with logs, but those rules actually don't flip-flop. Okie doke. Okay. So going back to just some basics, which again should be review. There's the basic transforming from log, and I like to phrase it as they're different languages. This is log language, and there's a way to translate it into exponential language. Yes? Just like you would translate English to French and vice versa. So the log language is as you see, what would the exponential equivalent to that look like? Haley? Remember from last year? You take the base, raise it to the other side, which would be b to the y power equals x. Huh? Oh, you had a cute little diagram? Alright. It's okay. Mrs. Zigai is much cuter than I am, but... Oh, was it? I am like the opposite of cute when it comes to making things creative. I would be the worst elementary teacher in the world. Clearly. Look at my room decor. That's not true. You're lying. Josh, you're on record. You can't take back what you're saying because you're being recorded. So Mrs. Zigai's going to have a huge problem with you. When she comes back in December. I hope not. All right, so, and back to kind of what we talked about yesterday, the base from the exponential standpoint always has to be greater than 0. The same is true, obviously, in log. It comes from the b base of the log. So the fact that both of those are b should be helpful. B is the base of your exponent. B is the base of your log. B also cannot equal 1. We talked about yesterday, right? For the exponential reason of a base being 1. And then x has to be greater than 0. Okay, so the stipulations that we ran into yesterday for exponentials are the same here in the log format. X has to be greater than 0 because you can't take the log of a negative, and you also can't take the log of 0. We just saw on the parent graph. X has to be greater than 0. So like I said, lots of connections to be made there between the visuals and the formats and the exponentials. All right, so here we're just rewriting each in equivalent exponential or log form. So this in log form would look like what, Winter, in exponential form? Very good. So x equals 25. And what would this look like going back to log form? Take a minute to think about that. I think that's probably the more challenging way. Zach, what do you think? Log what? Log base 3 of 64 equals b. What do you think of that? Just check yourself there, Zach. Your base is b, so 3 to the b power equals 64. That's not what that says, right? You've got these two flipped. It's log base b of 64 equals 3. That's the harder direction to go, in my opinion. I always just kind of write it and then double check it going backwards. B to the third equals 64. And then the last one, C. Nate. You're not Nate. It's the base raised to the other side equals the middle. What's the base? Okay, so it's the base, 3, raised to the other side. Correct. So we all can see here that y equals 1. This brings us to a property that we should know and that you guys actually use a lot. Log base 3 of 3 is 1. That's the whole reason that over here you guys learned to take, if it was 2 to some power, you took log base 2 of both sides. Because you did learn that log base 2 of 2 was just 1. Yes? Okay? So log base 3 of 3 is just 1, and you can, again, you can see from different vantage points how you've used that before. All right? Evaluating logs. So essentially, did Mrs. Zigai or your video talk about like the what power function? So, right, 2 to what power equals 16. So that's kind of how the state presented it to us, is called it the what power function. It's a cute way of thinking of it. I always taught it as, if you want to know what this equals, just set it equal to x, and then you're just solving to x. So you translate the base of 2 raised to the other side equals 16. So it just always reinforced your rule. Your base raised to the other side equals 16, and so x here equals, okay. On the next one, if I set this equal to x, that's a 25. So 25 to the what power equals 5. If you didn't know these by heart, you could use exponent rules to help you, right? 25 is the same as 5 squared, agreed? Right? Power to power means multiply. And then once you have common bases on both sides, you can just set the exponents equal to each other. 2x equaling 1 is going to produce x of 1/2. Does this make sense? Okay. And then the last one equals x. So b to what power equals 1. And this always, the log base anything of 1 is 0. And so these are the properties down below. So via that last example, we were just doing this. The log of 1 is always 0. Log base b of b is always 1. And you can check your exponent translation. B to the first equals b. That makes sense. B to the 0 equals 1. That makes sense. What's this one? B to what power equals b to the x. So there's log base b of b. People kind of think that that looks like, oh, they just cancel. They do. Log base b of b cancels. Again, we used that already. Log base 2 of 2 just canceled, and we just had y. And then here, what do you think about this one? If we change this to log power, it would be log base b. It's b, your base, raised to the other side, so that would be the other side, equals what? Right? B raised to the other side, that's what I'm looking at, equals what? X, right? To get these sides to be equal, our question mark would just have to be x. So again, that's probably more confusing to look at this way, but people like to look at that as the b log base b just cancel, and then that's just x. Josh? No. So really quickly, what's the answer to A? Kendall? Log base 4 of 4 to the 5th. 5. We're trying to take shortcuts here. Log base 9 of 9. Liam? Good. 6 to the log base 6 of 9. Stephanie? Good. And log base 8 of 1. Jalen? 0. So we went through that in obviously a little bit of a different order, but we got through it all. Any questions?